Okay. Okay, evening everyone. Okay, let's get started. So this week, we're going to introduce yet another data model, the graph data model, and one of the open source systems called Neo4j. Before that, just a little bit administrative. So we're going to release the group project instruction pretty soon on Canvas, as well as the data set. So it's a small group project, can have up to 2 students, and we don't form group for you. So basically, it's self-enrolled groups. You form your own group, and that will be set up on Canvas as well. So together when this is released. So usually the group name will indicate the lab you will demo. So we will have like SIT114 group 1, SIT115 group something. You can choose where, usually of course you have to do your demo in your lab, but if you form a group across the labs, you can decide which lab you want to go for the demo, indicated by the group names. So the project basically is like you're giving a data set, and there will be a few CSV files. They're kind of related with each other. And there are some target queries. So you need to design like a schema for 2 storage options, 2 storage systems like MongoDB and Neo4j, which is the one we're going to learn this week and the next week. And then basically for each storage system, you need to load the data. And sometimes you may have to write some script to load the data in the system. And then set up index and run target queries and record the result and observed performance. So there will be you will need to submit a report, and there will be a section asking you to briefly discuss the execution performance of a few queries. So yeah, in the report, you need to describe the schema, you need to describe your query design, and also the performance. There will be demo in week 10's lab, and you need to submit the script and the report before that. And even though it's a group assignment, we do try to work out individual contribution. That's the main thing in the demo. So we'll see if the members contribute equally to the project. So most of the time, everyone will get the same mark, which is based on the whole group's performance. But sometimes, if like one member is not really contributing, and like all the members are not contributing equally, so they may receive different marks. So that's all we will find out basically during the demo. Okay, any questions? Okay, yeah. Well, you can always ask question by sending me an email or posting a question on ad. Okay, so this is today's outline. So first, we will have a really brief review of graphs, and mainly the graphs in like programming language as a data structure. And then we'll see example of graph data. And you will find out, okay, actually there are a lot of things can be modeled as graph. And actually, nearly everything can be modeled as graph. And so there are examples, and then we will see how we can model graph data with what we've known, with the storage system we've already known so far. And then we'll introduce yet another very special model for design, especially for graph data. That's called the property graph model, and also it's the system that adopts it, and the query language. Okay, so here we're going to just give a very brief overview of graph as a data structure that you might have already learned in any data structure course, or basic programming course, basic programming unit, or like data structure unit. This is a very abstract view of graph. So it's just a collection of vertices and edges, right? And so it's something like this. It's very abstract. We don't really care at the moment what each node means or what the link means. But we know there's some relationship. There are node or vertices, and then there are edges between them. So there are different names, like vertex can be called node, or edges can be called arcs or links, but they are the same thing. And they're all pretty abstract concept. Okay, and usually we differentiate at the very top level, like two big categories of graphs, undirected and directed graphs. So it's based on if the edges have orientation, like if we can identify one as the source and the other as the target, like there's a point from source to target. So undirected is basically there's no direction, like an edge with A and B is the same as B or A. Directed basically means there's orientation or direction. So from A to B is like there is a direct. So it's like there's like a direction from or arrow from A point to B, and it's quite different from B to A. That's which is like the other direction. So in directed graph we differentiate these two, but in undirected we don't. Okay. How do we representing graph data? Again, when we say representing, it's like how do we represent graph in memory in a program, so we can easily run some algorithms on it. So the data structure we use to store graph, like in program, usually there are two popular ones. There could be, of course, there are other ones, but this one are the very popular ones. One is called adjacency list. The other is called adjacency matrix. Let's see for adjacency list, for directed graph, what it looks like. It basically storing the direct neighbor of a node. So each node is like, will have a list, and the list is basically its neighbors. So A doesn't really have any neighbor because it doesn't have any outgoing links, only incoming ones. But B has like C and F, so we put C and F there, and C is going to A and to C itself. We'll put A and C here, and D goes to E, and E also goes to D, and then F goes to A, so we put A there. So that's for directed graph. And for undirected graph, so again, for each node, we remember its neighbors, and because it doesn't really have direction, so here, so A has two neighbors, C and F, we'll put there, and B has two neighbors, C and F, so it's like this, and C has two neighbors, A and B. C has A and B, so we put it there, so on and so forth. So that's what we call adjacency list. We're just remembering like the neighboring node of a particular node, of each node. And another one is called adjacency matrix. It's called directed graph. Or adjacency, let's see the adjacency matrix for directed graph. So it's a matrix, and the dimension of the matrix depends on how many nodes you have. So here, if we have A, B, C, D, E, and that's a matrix of like 6, whose dimension is 6 by 6, and each row and each column basically means like here row means like the source, and the column means the target. So here from A, we don't from source A, there's nothing. It doesn't point to any target, so there's nothing. From source B, pointing to C and F, so we put a 1 in C, and it also points to F, so we put a 1 on here with the corresponding column of F. And similarly, C has C and A, so we put 1 here and 1 there. Okay, for undirected graph, because it's symmetrical, so we don't need the whole matrix. it will be exactly the same. So we only need half of it. And again, we remember the relationship. Like from A, we have C and F. From B, we have C and F as well. So this is basically how you read it. Okay, so all of these are very abstract level graph. So we only say this is a node, this is an edge, and we don't care what node means. We probably just give it a letter to indicate different nodes. Like this is node B, that's node F, but we don't really care what each node represents, and his edges, and we don't also care what edges means. So this very abstract thing can be used actually to model a lot of real-world data. And here, in the abstract one, it seems we kind of assume, because it's mainly because we don't care, like all the nodes is kind of represent the same kind of thing. Well, it doesn't have to be. Here, we want to give a letter to represent it because we don't really care what it means. But in real world, the node can represent very different things. Like B could represent one type of object, and F could be another type. And also the edges, we only just use a line to represent it, seemingly to indicate or implies they're not much difference, like from B to C or from B to F. It's the same type of relationship. But again, when we use graph to model real-world data, we don't really have this restriction. We can have the edges mean different things, but then that means we really need to add some meaning to the edges. We need to add the meaning to the abstract type now. Okay, now let's see a few examples of the graph data to give you an idea that graph is actually a very powerful representation. It can be used it's like to model nearly all sorts of data in the real world. Like social graph. So there's some data, it seems more like a graph. When you mention graph, there's certain type you might immediately think of, like the social graph, like relationship among people. It's like a typical graph. Or computer network topology. Again, it's like the node could be the computers, and then the link is just a network among them. So these are very like obvious ones. Or routing table, or road, rail, and airline networks. So these are a few of them. And in addition to like the very typical things that you can think of, and in particular like social graph and other things, you can actually model a lot more richer information using graph. So let's see some example, like social graphs and its extension. So this is a very typical social graph, like most people will think about when we talk about social graph. So it consists of like users, right, and their relationship. Could be like users follows another users, like Twitter users, like one user follow another users. This is a small and very simple social graph, and it's like exactly reflecting the abstract ones we've seen. So there's one type of node, they're all users, and there's one type of relationship that like follows relationship. But the graph is not really restricted to this type of simple usage. We can actually extend the graph by adding different types of things, and we can use it to model related data, related information. So first, like nodes do not have to be of same type. So we can have node representing user and also node representing a message. And we can use edges to represent their relationships. Yeah, edges can have different meanings. Could mean follows, like between the users, the edges could mean follows. And between a user node and a message node, it could be something like current or previous. So here we have between user and the message, there's like current. And among, like between message, we might want to know which message is like the order of message. So we can use edges. This is like a linked list, right? So the order actually has some meaning. Okay, so we can, so even if we can model even more complex social graph, so we might only have one type of users, but we can have very like richer set of relationships among them. So like, and also we can have multiple edges between the same pair of nodes. So that's yet another extension of the very generic graph concept. Like between these two users, they could be friends of each other and they could be colleagues of each other as well. And also between these two users, they could be friends with each other, and also one user could be the boss of the other users. So there are multiple relationships. So we to represent this, we add multiple edges. And so graph can also be used to model other things that doesn't really look like a graph in the first sight, like transaction information. So this is probably more like an object diagram, right? If you ever did any requirement analysis, you try to understand the relationship of object in a domain, you probably have drawn something like an object diagram, and eventually you convert that into class diagram. So this kind of diagram is actually also a type of graph. Here is like if we want to model transaction information, and the transaction consists of users and the orders user placed, and each order can contain lots of items. So there are like quite a few objects. That's three types of object or entities. We have user, we have order, we have items, and they have some relationships. Like the user can place order, and a user can place many orders, and we also want to be able to find what is the most recent order. So we can add a relationship here. So this can if you're doing like an object design or class design, this will kind of suggest you, okay, in the user class, you probably need to have like a variable to remember all the orders the user has placed, and you need another variable to remember like the most recent one. And order can contain items. So yeah, each order usually consists quite a few items, and then so item is also because item has like the item ID, the description, and probably a few other attributes. So it's a type of entity. And also, we might want to have some kind of, we want the order because the user can place multiple orders, and we really want to remember to have an easy way to see which order is placed before the other order, without really looking at the time, the date in it. So we can add a link, we can add an edges between the orders, like previous. So all of these are like the different, like the real world usage of graph, how we can like model different things as graph. Okay, so now let's see how we can actually store this data in a storage system. So far, like here, when we talk about this adjacency matrix or adjacency list, it's mostly like, okay, we already load the data in the memory, and we want to organize it in memory. Now it's more like, if we have a lot of data, we need to persist it on the disk. so that we can retrieve it, like running queries. So how can we do it? Well, there are many ways of doing it. So it doesn't really matter what you want to represent the data in the program. You can always store it in a different way. Remember, the physical one and the logical one could be quite different. So we can store any graph data in relational model, actually, or in MongoDB model. So first, let's see example of how we can use like a relational database management system to store graph. So graph basically contains links, right? So it contains the node and links. For node is very obvious because node is a type of entity, and then for the entity we usually need to have a table for it. And for edges, particularly if the edges is like a many-to-many relationship, and then usually we need to store this in a separate table, like a link table kind of thing. So here, suppose we want to store social graph, like who is the friend of like a person, and then which person is another person's friend. So first we have a person table. It stores the profile of person. It could have a lot more columns. Here we only show 2 columns, like the ID and the actual person's name. And then if we want to remember the relationship among the persons, like the friendship relations. So the easy way is to create another table. This table doesn't need to have a lot of attributes. It only needs basically 2 attributes to indicate the link. Because link has a source and a target part. So this is person ID and friend ID. So indicating, okay, person 2 is the friend of person 1. Yeah. So for any pair of friends, we have a row here. So this says person 1 is also the friend of person 2. But sometimes assuming there's a directed one, it doesn't have to be always like if person 1 thinks person 2 is friend, person 2 will always think person 1 as friend. So if there's like a reciprocal relationship, we store it twice. Okay, so we can write database queries to answer questions like, okay, who are this person's friend, like who are Bob's friend? But to be able to do that, we need to get information from the 2 tables, right? So which means we need to join them using the IDs. And here, because we want to find out the friend's name, so we need to basically join twice. First is we join this ID with the person ID to basically find who are the friends of the person here. So if we know like Bob's ID is 2, and then we try to find out, okay, by joining this, we are able to find out, okay, the friends are 1 and 9, right? And once we find out this friend's ID, and we also want to find out the friend's name. And to do that, we need to join, we need to perform another join, and this time it's the friend's ID with this ID to find the name. So we need to do another join. And this is what it looks like. Now, if we want to find out who are friends with Bob, so it's asking the other way around, assuming the friends relationship, again, as I said, has directions. So we still have to use these 2 tables, and we still have to do 2 joins, but the order is slightly different. Now, because we want to find from here, so like the Bob is here, and then find out the friends of Bob, then we need to first join. When we do join, and it's on these 2 columns, and then to find out for when the ID is 2, like Bob's ID, and who are the other IDs. And once we find this out, because we want to find the name, so we have to do this. We have to do another join this with the ID to find out the name of the person indicated by those IDs. So that's, again, 2 joins. Now, if we want to find out who are Alice's friends of friends, in that case, we still, because we still have to to do the join. Now it's more, we have to do more join. First, we do one join to find out Alice's friends. And we do another, we have to join this. We do a self-join to find friends of friends. And then we get all the IDs, friends of friends. And once we find that out, we have to yet another join to find out the friends of friends name. So there are three joins. And you can imagine if we want to spread even more out, like after like 3 degrees friends, and then we have to run more joins. We have to yet to do a self-join here. So it will become pretty complicated, and it's error-prone. So that's the relational way of doing it. Let's see if we can use if MongoDB can make things a little bit easier, because remember, for a relational database, to satisfy all this normalization rule, we have to put data in separate tables. But MongoDB are not really restricted by that, so we can save things in the same like collection, and this might actually make things a little bit easier. Now let's see, like for MongoDB, we don't really need 2 collections here. If we only want to remember to store like a person and the friendship among all these persons, we only need 1 collection, because we only have only one entity, which is person. And for each person, we give it ID and then like the profile, the name could be others, and then we'll have the friends can be easily saved in an array field called friends, right? So this means ID2 is person Alice friends, and here means, okay, for person Bob, it has 2 friends, 1 and 99. And for 99, it has person Zach, it has 1 friend, which is with ID 1. Okay, so still, let's see how we can run queries to run the same queries on MongoDB to answer the same question. Who are Bob's friends? So first, we can find out Bob's friend's ID. That's a simple query, right? So we just find when the person is Bob, and we only want to get its friends. So we have a query condition and a projection, but we can't here. We only get the ID, and to find out the friends, we need the actual name. We need to run another query. So we still need to use 2 queries. So we can do something like this, or use a very simple one, like in operators. If we already find out, okay, this one has 2, like as an array with 2 elements, so we can run a simple query like this to find basically find the name of these 2 IDs. And of course, you can use variables to represent it. Now, if we want to find out who are friends with Bob, first we need to find Bob's ID. It's 2. And then we find out the person that are friends with Bob. So we find like, okay, friends include 2, and then we find out the person. So that's, again, another query. So if we want to find all the document with the friends fields contains 2, and here is this one. And the friends of friends is a bit more complicated. We need to find, okay, so we just need to run a few queries. First, find Alice's ID, and then find out Alice's friend's ID, and then find out the actual person. I think I actually need another query here to find the friends of friends. So here, you might need to run a few queries if you are using an early version of MongoDB. And then MongoDB also discovered, like, okay, doing this kind of graph search is quite a common type of query. So since 3.4, it actually added a new aggregation stage called graph lookup to help us to run this type of finding like friends of friends of friends query. And so instead of using the find query, we can use aggregate. It's a graph lookup. The syntax and the way to do it is quite similar to the lookup, which means you're doing a join. So this again, we need to do some kind of join. So here, if we want to do like to find out Alice friends. First, we have a match stage to find Alice, and then we do a graph lookup. And again, graph lookup can bring in another collection. So it's like from person. So now this is like bringing another collection, just like you do the normal lookup. And then you need to say like, okay, now we're going to do the graph traversal. So how do you want to start your traversal? So we're saying we want to start with friends. So first, let's see the output document will be quite similar to the lookup stage. It basically will, for every document in the input stage, it will output a document, and it will keep all the original fields and will add another fields to remember the graph thing. And this is how you indicate, like as is like, okay, I'm going to add a new field, and then here you specify the new field name, and this is a new field, and this field it basically contains all the graph traversal data. And then how do we construct this? So in the normal lookup, this only contains the document from the other, the matching document from the other collection, right? So here, what we put here is a bit more complicated to work out. It's still the document from the other collection, but how do we match it? How do we find the document? It's from all of this. So this few fields will basically indicate what should be put here. Like how should we find the matching document from the other collection? So first start with is like how do you want to start the graph traversal? So here it says start with friends. It's like, okay, from, and this is a field path, right? So indicating we actually want to get the value of these fields. So it's like starting from here, and we want to start from the value of this field, which is 2. Okay, and then after we starting from 2, and then how do we find things? So we need to use this, and then to match. So the connect from field and connect to field is like, okay, we want to use the field from here and then the match field here. So use this to find as a value to find from the other collection, and the value equals like from this field. So here, like, okay, now 2, and then basically we find this one. And then the depth also means how far away you want to go. If the depth is 0, like we stop from here, it's like immediate one. But if the max depth is 1, like we should go one step further. So now we're starting from, once we find this, and now we're starting from this, like it has 1 and 99, and we try to match 1 and 99 with the ID 1, and then we can find these 2 things. Find 1 and 2. And here we actually we also indicate, so it's not just the document from the other collection, because the other collection only contains name and friends. We also add another field, which is depth. So this will give you an idea. Okay, depth 0 means immediate friends. It's like this is immediate friend, which is Bob, and depth 2 is like friends of friends. So it's like from Bob, we find these two, like ID 1 and ID 99. So we find these two. So once you have this, and you can have further query, like if you only just find immediate friends or friends of friends or friends of friends of friends, that means if you put a maximal depth 2, you will have quite a few other documents, and then with the depth equals 2. Or if you want to find all of them. So this you can have like further stage to query those ones. So that's graph lookup. It's not that easy to write, right? And once if you want to find a lot of things, and this will become actually quite complicated, and it will be really big document. Okay, so in summary, it's pretty possible to store graph data in various storage systems. So, well, if you don't need very complicated queries, maybe you can just use whatever you have, whatever you're familiar with to do it. So this is like if it's just shallow traversal, like only find immediate like links. That's fine. It's relatively easy to implement. You probably only need a few joins or write a few queries, and the performance is pretty okay. But if we want very deep traversal or traversal in other direction, and first it's quite complicated to implement, right? Like in relational databases, you have to write a lot of joins, and it's very easy to make mistake, like which one should be what should be the key to join, or like multiple queries again. So that's a bit complicated, and will be less efficient, in particular if you join so many times. And it's very error prone. Once it gets complicated, it's easy to make a mistake, and it's really hard to actually find out you made a mistake. So if we do have more complicated, we really want to traverse the graph in a complicated way, like very deep traversal or traversal in like a reverse direction, we can use other ways to do it, to like more native way. So let's see what's the property graph model. But before that, let's see. There are some special techniques or technologies for graph, and there are two big types of it. We're only focusing on one. One is called graph processing. So basically, it's more interested in like implementing complicated algorithms on top of graph data. So it's not really about how to store it. So the data can be in any input format. Could be in a database, could be in maybe plain text files, or other things. And then we can, most likely, we probably just load all the data in, and assuming the data is not that big. And then we try to perform graph-related like processings, and like online analysis processing of graph data. It's more like we want to do this kind of an analytic kind of thing. The graph itself probably is more or less stable. We don't really need to change the structure, like add a node or add edges. It's relatively stable, so we can probably save it in just like even text file would be all right, and then we read it in those input format, and then we try to analyze the graph. So there are a few of such systems, and the other one is the one that we are more interested is the graph database. So assuming that the data is not like stable, so we will keep like updating the data. So there will be new nodes, there will be new edges, and the node might be get deleted or updated. So it's a very dynamic graph. And so we want to have a way to be able to easily manage it, store it, and query it, and also have run some simple process on it. So that's the graph database. And so it's more like it's a storage engine, and it supports graph data and supports high-level query language. And usually, because it's called graph database, not like generic type, so the storage should be quite native to the graph data, like specially designed for graph data. And it usually supports both the online transaction type of data. Transaction type of processing is like we need to update. We need to query a subset. We need to update the graph constantly. And it also can do OLAP, like an analytic type. We want to analyze the current data. So we're focusing on the graph database, as I said. And for graph database, before designing any graph database, one thing you work out is how to represent like graph as data, not like in the memory and like using data structure. So it's more like a data model. So again, there are two relatively standard or typical models we can use to describe graph. And we do have systems that work around these two different models. One is called RDF. That's more like an early version. It's more standard-based. It does have a lot of specifications for it. Resource description framework model. It was not really initially designed for graph, but was adopted in the community as like a pretty good way to do it. So it can be the node and edge relationship can be modeled as something like a subject, predicate, and object. Subject and object are like the node, and predicate is like the edges of relationship. So, and this one also has a standard language called Sparkle query language. And there are quite a few examples of it, but we're not going to cover that at all because this is actually not that natural. Sometimes to be able to model things as this subject, predicate, and object, you do have to do some kind of, it's not like a direct mapping. And the other, which is more, even more native, is called property graph model. This is not really standard based. It's actually more, it's more flexible. It doesn't really have like specification to describe things because it's pretty intuitive. So it expresses node and edges just as object like entities. Both can have properties. So it's very intuitive. It doesn't really have, and it doesn't really have a standard to tells you what you should do. Well, these are more standard-based. And there are various query language, and again, the query language are designed by the systems. So they can use the same model, but they design their own query language. So we have quite a few, Apache Titan. So it supports various storage engines. So this again, it tries to separate the storage engine with the logical data model. So the logical data model is property graph model, but the storage engine can be just like Berkeley DB or Cassandra or HBase or others. And it has a query language called Gremlin. And then there's another one, which is the one we are covering, called Neo4j. And Neo4j doesn't really separate the physical model and the logical model. It actually provides a very native storage for the graph data. So it has its own storage model. And it has a language. It's called Cypher, which we're going to learn today. Okay. So what is property graph model, and it's proposed by Neo Technology, which is the one that behind Neo4j. There's no standards, definition, or specification. As I said, the model itself is pretty like intuitive, self-descriptive enough. It doesn't really have, you don't need to learn a lot to understand it. So first, it's like there's concept of node and edges, and both of them can have properties. So that's pretty natural. Well, the RDF model, it cannot really express the edge property in a natural way. So sometimes it's really hard to convert a real-world model as like an RDF way. But the actual storage will varies, and the query language basically varies, as you already seen. There could be Cypher, there could be Gremlin. So it's something like this, just like all the graph you've already seen. So we have node. Node can have property. That's another node. And we have edges. Edges can also have property as well. Like pi knows Richard Parker, and pi has the name pi, and the name h is 14, and the Richard Parker has a name. And those relationship can have a property like since 1 year, and they have a common interest, which is sailing. So basically, that's it. Okay, I think I'll give you 10 minutes break, and then we will continue to see what's new for J. Okay. Okay, can you come back to your seat? Okay, we will continue with the lecture. Okay, so Neo4j is like is a quite popular open source graph storage system. In particular, it provides like native graph storage, which we will see next week, the actual storage organization. It does have a few interesting properties like index-free agency. It supports index and replication. And, but again, similar to MongoDB, its database engine itself is not really distributed. So it's like a single node one. But it does support replication and a few other things. And its query language is called Cypher. It's just Neo4j use it. It's not like a standard one. And similar to MongoDB's query language. So it's just like proposed by Neo4j, implemented by them. And there's no standard for it. And it's not really based on relational algebra or anything. Okay, so the property graph model as in Neo4j, it's similar as a general one. It has node and relationship. Node contains properties, because node is like the entity, so it's like an object. It will have properties, right? And each property is like has like a property like name and then the values. So it's like a name and value pair. And a node can have labels. In a sense, it's like a classes, but it's much more lightweight because you don't really need to define what a class needs to be. And a node can have multiple labels, and the label is pretty flexible. Basically, the label is just a name. It doesn't have its own property or anything. And you can dynamically add or remove labels. So it's like a classes, but it's much more lightweight. Doesn't have its own definition, except a name. The relationship, then there's relationship, and it's used to connect nodes. It has a direction, but we can also use it you can also ignore it, basically, if you're modeling an undirected graph. But it just gives you the direction. And it has an optional type. Again, it's like a class of the relationship. And a source node and target node. So each direction needs to have a source and target node. Can be the same node, but it can't have like a node with a relationship with no target node, only source node, or no source node, only target node. That's what we call dangling relationship. So this means like when you update the graph, in particular when you update involves like removing a node, so you have to make sure you need to remove all the relationship attached to the node. Otherwise, that relationship becomes invalid. So what is property? Is basically like attribute or property. So both node and relationship can have it, and it's very useful in modeling and querying based on properties. Okay, so this is what it looks like. Again, it looks very much like the graph we will draw when we're doing like a system analysis or system design. Try to document the important object in a system. So this shows like three entities, like two persons and one movie. And each with a set of properties like name and born, and the movie has title and released. And there's also relationship. So we might have between the person and movie, we can have acted in relationship. And in acted in, we can add a property called roles. Because when a person acted in a movie, we also want to know what's the role the person is taking. And also we can have another relationship. One person can be director of a movie, so this relationship is directed. And this one probably we don't need a property. Okay, so nodes, they're often used to model entities, right? It's pretty intuitive, like objects in the domain. And has property and label. So label, as I said, it has some similar, can do similar things as like class, So it's a way to group similar node, but it's much more lighter weight because you're not restricted to belong to like a particular type of label. You can have multiple labels, and you're not like the label is not a permanent thing. It can be removed easily. It's pretty dynamic. So well, class you can't be that dynamic, right? Once you create an object of the class, you basically just belong to the class. So it's very dynamic and flexible. So it sometimes can be used to tag node temporarily, like we want to say this node is like suspended, or that particular item is on sale, but only for this period of time, and after that we can remove the label. So it's like here, this is a node with like two labels and two properties. The label is person and actor. So it's both a person and actor, and the property is like name and born. Okay, relationship, it connects two nodes, like source node and target nodes, and the source and target can be the same. Always has a direction, and again, you can ignore it. And it allows traversal happening in both directions. So physically, there's a direction, but it doesn't really, logically, you can ignore it, or you can, it doesn't mean you can only go from one direction to another. You can go the other way, you can reverse it. And it can have a type, and doing similar thing as like the label, like grouping similar properties, a similar relationship together. And it can also have properties like this. A relationship can be of the same node, or like this. From this to this acted in a movie. A person acted in a movie. Source node and target node. That's the property, and that's the type. Okay, so a property is basically like a pair of property key and property value. So it's like attributes, which might be a more easier thing to understand. It's like attribute. Attribute has a name and a value. You know what you see. Name is like the property key, and the value can be of different types. So similar to MongoDB, Neo4j support different data types, like simple types, number, integer and float, or string or boolean, and it can also have spatial type. It can have quite a few temporal type, like date and time. And again, the set of date type may grow in each different version of the Neo4j. So here are just a few common or typical ones. Okay, so there's another important concept. It's more like a logical concept. It's called a path. A path is like one or more node with connecting relationships, and it's typically used when we need to traverse the graph as a query or a traversal result. So a path have a source node and a target node, and it can have one or more relationships, or even zero. That's a path of one. Like a one node is also like a path of length 0. And this is like a path of length 1, so it's one relationship. And we can have paths of length 2, of length 3. So anyway, a path is like from one node to another node. In between, there could be a few other nodes and relationships. Okay, so that's the very basic things. Now that suppose we have a data model like that. We have many nodes, and we have many edges. So how can we query them? How can we find the subset of interest? So let's see the language. So it's a language specific to Neo4j. At the beginning, it might look a bit weird, but then when you get used to it, you will find it's actually pretty powerful. It's relatively easy to read and understand. So there are a few key things we need to know before we start writing the whole, like the query statement. So first, it uses something called patterns to represent core concept in the property graph model. So when we say core concept, that means node, a relationship, and the path. So all of this has a pattern. You can represent them. So a pattern may represent that a user node is having a transaction with the item formula in it. And then there are basic patterns representing like nodes, relationship, and the paths. And then using those basic ones, you can form more complicated patterns. And then the query is like you try to see, it's like a pattern matching. So you try to see from your actual data some matching things of the pattern. And then it uses clauses to build queries. So some clauses are pretty like borrowed from SQL. Even it does similar things as SQL, but probably not in the same expression. And a query may contain multiple clauses, and which we will see later. And then there are functions, like can be used to perform aggregation and other type of analysis. Okay, first let's see how do we represent a node. The very basic pattern. Single node is just pair of parentheses. And usually we give an identifier or variable. So something like this. This means a node n. N is a variable you give to it. And the variable has a scope. It's only restricted in a single query statement. So it's just like the variables in any programming language. And it has a scope. It's only in this particular statement. So in other statements, you can't really use it. And again, we will later on see how we can use it. And if you don't use a variable, that's okay. It's just a pair of parentheses. That means like a no-named node. And we can add labels as well to indicate we want a pattern representing a particular like a type of node. So here is like means okay, like this represents a user node, and this represents a node which is both a user and admin. So using a column and the label name and indicating the labels, you have multiples. Basically, you just put them together. And we can specify properties as well. Basically, within the parentheses, you can put a lot of things in it. So it could be a pretty wide parenthesis. Like here, it says, okay, we want to find a node, and the node has a name, Andrews, and has a spot like this. It might have other property which we're not very interested in. So this one will basically match a lot of any node, right? And this matches a type of node. And this matches probably one or a few nodes. So some patterns are more general than the others. Okay, well, relationship. Relationship is expressed as like a pair of dashes, like this. And you can add arrows to indicate direction. And the basic one is just dashes, like undirected. So it always needs a source and a target node, like this. Here I say directions are not important. So this means a very basic relationship between A and B, between two nodes. And we don't even care what type of node it is, just like any relationship between two nodes. And sometimes you want to give because relationship is also data, right? And you may want to refer to it later on, so you can give a name to it. And the way to give a name is put the name in a square bracket and in between the two dashes. So here it's being, okay, relationship called R, and it's from A to B. Now it has directed. So we add an arrow, so it's like from A to B. And so this is pretty general. So these two basically will match the same thing. The only difference is now we give a name to it, so we can refer to it later. But actually not the same thing. This has an arrow. Anyway, so sometimes you want to be a bit more restrictive. You want to say, okay, I'm only interested in a particular type of relationship. So you can also add the type there in the same way as you add the labels to the to the node by adding this column and then followed by the relationship type. So here is saying this represents a relationship between A and B of this REL type. And sometimes we want to specify a relationship that may belong to one or a set of types. So it could be either type 1 or type 2, we don't care, any of this. So you use a pipeline to a character to indicate this. So this basically says a relationship between A and B, from A to B, and it could be type 1 or type 2. And so this is basically the same as that. It's just now we don't give it a name. So we're not interested in the name. So again, a relationship from A to B of type REL type. So whether or not to name a node or relationship really depends on if we want to refer to it later in the query. If you're not interested in it later, you don't need to spend time to think about a name. So this is direct relationship, like they're direct neighbors A and B. But remember, we also, like for graph database, we are also interested in like more in-depth traversal, like not just direct relationship. It could be the friends of friends of friends, like a long path. So how do we represent that? So there's, again, we can add something in the square bracket to indicate it's a relationship with certain length. So this, by adding a star, it means the relationship of some length. Here, if it's just a single, after a star, it's like a number, so it means, okay, a path of length 2 between node A and B, so we don't care what is the other node in between, but we want to find from A to B, and then the path is like 2. So from A and B is not directly related. So from A to B, and then going through another node. It's actually equivalent to this, but much shorthand version. You can write it as this or as this. So this is like a fixed length, but it can be a variable length, like you specify a minimal 3, a maximal 5, so something like this. Or it can be omit one bound, like minimal 3, don't care, it's maximal, or maximal 5, don't care about minimal. Or sometimes we omit both bounds. It's just like so this is the more general one. Like we want to find some paths between A and B, we don't care how long. So it could be like 1 or 2 or 3 or up to the maximal one you can find. Okay, so let's see the pattern example. So the pattern is supposed to be, will be match the real thing in the graph database. Let's see example of pattern matching. So if we have a pattern like this, so basically that's a very general pattern. It matches all nodes in the graph, any node in the graph. So all of this matches because it doesn't give any conditions. Now, if we have a pattern like this, so with a label, so that means it the pattern represents like a node of the movie label. So now it only matches this one. And now if we have something like this, it matches a node which has a name called Tom Hanks. And then again, most likely, in this very small graph, it matches a single node, which is this one, with a name called Tom Hanks. Now if I have a pattern like this, so it's a relationship from P1 to M1, and we don't care, but there is a relationship of type directed. So this whole thing, this pattern matches this path from person here to the movie Forrest Gump. And the query basically is trying to find this, is doing pattern matching. And you specify the pattern, and then the database engine will try to find the matched patterns from the database. And yeah, once we find the match, and then we give the variables here. So this node is referred to by variable P1, and this is referred to by variable R, and this is referred to by variable P2. And later you can specify them. Like if you want to return P1's name, or M1's title, or R's something else, then you can do that. Okay, now let's see the clause, the actual clause or statement. This again, we do like a CRUD, create, update, retrieve, and delete. So create, how do we create something in the database? So we can create nodes or relationship with properties. Like here, we create a node called the matrix1 with the label movie. So here is like within the, so this whole thing is a pattern representing a node, right? It's representing basically a whole node with all the properties in it. So it's of the label movie, and we give it a name matrix1. And this node has 3 properties: title, released, and the tagline. And we give the node identifier matrix1 because we can refer to it later on in the same query. And then we create another node called keyNew with the label actor. So again, it's like a full node. It has the type, it has the label, and it has 2 properties. And again, we give it a name. And then after we create 2 nodes, we can create a relationship. So we create a relationship. So this between the node keyNew and node matrix1. Matrix1. Then we create this relationship of type acted in, and it has a name called rows, and then it's neo. Now this, remember, we are using this to identify our variables. keyNew refers to the node we just created, and this refers to the node we just created. And so because we give it name, so we can use it in this clause. Otherwise, we have to find them. But we didn't really give a variable here because we're not interested in using it later. So we just say we want to create a relationship, and we don't give it name because we're not using it later. So how do we make sure that the scope, it still is within the scope? Like when we write this statement, like this clause, this variable still refers to the node we just created. So what we need to do is we need to put all of this in the same statement and run them in one go. And then here, then the variable will be referred to still within the scope. So just put all of this together. If you run them one by one, then you basically, this one won't be able to, the variable scope is like already out of scope. So it won't refer to the node we just created. And that's why in the lab, you will see there's a huge create like a statement with all the creations written there, because they want to refer to things they just created. So that's create. This is relatively simple. Now let's see. The query is usually there are a lot more variations. So we start from the very simple one. If we don't only want to find something, so this is a read query. The very simple one is like this. Because it's a pattern matching, so we usually start with the keyword match and followed by a pattern. And then after you match, you want to return something, right? So there's another keyword called return. So that's the very basic component of a read clause. And now, of course, you can have more, but these are the two most important ones. You match a pattern, you return something. So usually this is this is like select all statement in RDBMS. So it's not really selected because we only find a node, but so this is return all the nodes because we don't give any. So this pattern is very general, match all the nodes, and then we want to return them. So this one is like return all nodes with a given label. So it's like select something from movie if the movie is out like a particular table storing all the movies. So here we put this here. So now see these two, when we give a variable here and then we can use it here. So match and return and match movie and then return movies. So this one returns all actors' name in the movie The Matrix. So we match this one. So we have actor, we have acted in, and then we have a movie with title. And then we return a.name. So we only give the actor node an identifier or variable a, so we can use it in the return subclause. But we're not interested in this. We're not interested in the actual movie, so we don't give them any names. Yeah, here a has a variable and it's used here, but we do not need to return the relationship. So there's no name. It starts with a column, and we don't need to return anything about the movie. So again, we don't return it. Or we don't give it we don't bother to give it a name. So only the actors we are interested. So we give it a name, and then we can refer to it later. Okay, so that's the basic one, and we will see a more complicated read query later. But before that, let's see the basic update. So update, again, usually you're not going to update everything. You have to have some condition then to find certain things and then to do the update, right? So it usually also starts with a match statement. And then following by like what do you want to do, actions. And then you may return something, but sometimes you may not return anything, that's fine. So here, this is like, if we want to set the age property of all actor nodes, like originally the actor nodes only has born. If we run this query in 2014, and we can work out the age, right? It's just 2014 minus the born year. So we match all the actors, we set the age to this new value, and we can return it so that we know we can have a look of the updated one. Or we can remove a property. So that's the set can be used to update the existing one or add a new property. And to remove one is like this. Again, we match something, we remove age, and then we return this. Or if we want to remove a label, yeah, it's possible. Remember, as I said, like label is it's something very flexible. It's very dynamic. It's not like once you get this label that you're permanently attached to you. So we can dynamically add or remove labels. Like when we match this and we remove this, so this is how you indicate the label. And again, you can return to see the updated ones. Okay, so delete. Similarly, it starts with match because again, you want to find out the things you want to delete. So delete relationship is relatively pretty straightforward. You match a relationship and then you delete it. So we want to find like remove all the acting relationship of Keanu. Then that's how we find it. We don't care which movie it acted in, but we just want to remove the relationship. So we delete this. But removing a node, as I said, because you can't, because removing a node and then this might leave the relationship become like incomplete it might missing a start or like source or target node. So removing a node is not like you just remove the node itself. You have to find all the relationship attached to it and remove both of them. So it's like this. If we want to remove a node, like the movie node, and then we can't just match this. We actually have to match all the relationships. So here, because we have to match everything, so we don't really specify a condition. And again, we don't care the relationship is to what type of node. So we use empty parentheses. And because we need to delete the relationship and the node, so we give both like variables, and then we can delete them. So we delete M and R to make sure the graph is still like a valid graph. Now, sometimes just using the patterns might not be very effective to represent the type of condition you want to find. The type of condition you want to have in the data you want to retrieve. So we can also use the where clause, like match n, where the age is less than 30 and employee is greater than 3. So that's whatever. So that's a pretty handy way to specify the property of the node, and then you can return that. And then there are many functions that we can use as well. In particular, we're focusing on the type of function that will help us to run aggregation type of queries. Remember, that's something very useful and very important in any storage systems. Instead of retrieving, like matching something and retrieving the data as is from the database, we sometimes actually want to run some aggregations to get some statistics. So this can be done in Neo4j as well, using built-in functions, built-in or user-defined functions. There are actually a lot of built-in functions. And again, you can imagine the set that will grow with each new release. We're not going to cover all of them. We're more interested in aggregation function. And while we are discussing aggregation function, we will see a few other functions as well. Okay, let's see how do we use aggregation function to achieve this aggregating behavior, like group by, which is a very typical thing you want to learn. So we can use, usually once you do group by, you want to count, right? Or you probably want to sum up some properties, or you want to find the average, you want to find the minimal maximal. So all of this has a function to represent it. And we can write a clause to do the group by, and then to return like whether a count or sum or average. Okay, so how do we indicate like grouping key? So group by is like by something, right? So this is kind of implied in the return clause. So it takes a bit understanding to figure out how to write it. So how do we do it? Usually, it's not really specified explicitly, it's implied. It's not like in MongoDB or in our DBMS. The group by like attribute is clearly indicated. So here is more or less like implied. So in the return clause, there will be quite a few things. So anything, the thing that is not aggregate function is considered as the grouping key. So if we have something like return n and then count something. So count is, remember, this is a aggregation function, and n obviously is not. So it's something in the previous clause. At the moment, we don't know what. But when the database engine sees a return clause like this, it knows, okay, n is the grouping key. And so we're going to to group the result based on the nth value, and then we do a count for each group. So for instance, this is an example. If we want to find out like the gender distribution, like how many male, female, or other genders in the database. So this is how we can do it. We can still we're only interested in the person node, and we want to find distribution of the gender. So the grouping key is the end of gender. It's like the value of the gender property. And depending on how many values this property can have, how many unique values this property can have, and then it will return that many groups. And each value represents a group, and then we count the number of nodes in that. And again, like sometimes we don't need to do a grouping. We just want to return statistics of the whole thing, right? So that's also possible. Basically, in your return statement, you don't specify anything that is non-aggregation function. Like here, if we want to count the number of person node in the graph, that's how you do it. Just return count star. I mean, we match. First, we find all the person node, and then we count them. There's no grouping. There's only a single group. We return a single value. Okay, so let's see a few examples of using aggregation to run this group by thing. If we want to find out the earliest year a person was born in the database, like the oldest person, basically. So this is, again, so we do like a filter, a match. We only need the person node, and then again, we're not really going to group it by anything. So it's like a statistic of all the result. So we only put aggregation function here, which is minimal of the born year, like the earliest year. So that will return the earliest year. It doesn't return the person, actually return the earliest year, like anyone that's born. Okay, and you will find out sometimes you can use this to do things that probably sounds a bit impossible, but still able to do that. Like we can find out the distribution of relationship type belonging to nodes with certain features. So the grouping key is quite flexible. It doesn't have to be like a property value. It can be like something like this. It can be actually another function, but this function is not aggregation function. It's a scalar function. It will return like a value. So we match like so this is a pattern indicating like path, right? So the path has a starting node with name equals to A, and then we don't care about the target node, and then we don't care what sort of relationship is, but anyway, so it's like any relationship of this node, any relationship of this node, and we want to find out, maybe there are many different type of relationships, so we want to find out the distribution of type. So this is, we can work out the type of R. So we give it R, type of R, and then we count like for each type how many relationship instances there are. So this is the grouping key, and this is the aggregation we're doing. Okay. So for certain aggregation functions, we can add like keywords in it to like a modifier to slightly change the behavior of the function. Like the distinct is one of this modifier. So for instance, let's see this query. So we want to query like this is the pattern, right? So it's like we want to find a relationship between a person and another person and yet another person. So it's like friends of friends. So this is the direct friend, and this is the friends of friends. And so here for a particular person with name equals to 8, which is this person, right? Name equals to 8. And then we have friends and friends of friends. And we are interested in counting the distinct friends of friends, because after many levels, there could be like a duplicate, and we're not interested in a duplicate. So we can use a distinct to modify the count function. So we count the friends of friends, like count this. This is another, so we can put more than one aggregation functions here. It doesn't really matter. It will just, each will do its own counting. So this is count distinct, this is count non-distinct. So when we have this pattern, it actually matches quite a few things. So first, we find, this is the person, like where MEA equals A, and this person. And then we do the matching. So that's one match, right? So that's one pass that matches this friends and friends of friends. And then we have another pass again, like this person and the friends, and then this is the friends of friends. And then that's it, because this one doesn't really point to anything else. So we have two paths we have two actual paths that match this pattern. And then the friends of friends actually refer to the same thing. So these two paths, the middle friends is different, but the friends of friends is the same. So if we run something like this, and then the distinct count will give you 1, so just one distinct friend. But if we don't care about distinct, and it returns 2, because here it's like we find 2 matches, so it returns 2 here. But if we're keen, we don't want to count duplicate, and you use distinct, it will say actually only 1. Okay, so sometimes if we really want to, if the query is a bit complicated, like the condition is a bit complicated, it could be like we want to find something, and then based on that thing, and then we want to find something else. So in that case, like there's subqueries. So again, that's quite typical, and of course, Neo4j is able to do that. So there are a few different ways you can kind of connect a few clauses together to make a query more complicated. So this is like we can use the with clause, doing similar thing as with in SQL. Mostly used to apply conditions on aggregation result. Like once we've done aggregation, we found some result, and we can use that result as condition to do further filtering. Or it can be used to modifying, like ordering, limiting the result before collecting them as the list. So for instance, if we want to find the person who has directed 3 or more movies, and so first we need to find all the persons who has directed a movie, right? Some movie, and then we need to count for each person. Now this is a aggregation, right? And the grouping key is the person, and we want to find how many movies, count the number of movies directed, and then return. After that, we need to apply another one, right? So we only return the person with, like, movies is greater or equal than 3. So we run another further condition here. So we use the with clause to basically bring down the result of previous query, and then to be used by the next one. So instead of return this directly, we use with. And the way to interpret this, it's similar as if you just directly return it. But here we're not really returning it. We consider this as intermediate result and can be used by further queries. Or if we want to return the oldest 3 person as a list, so we can do something like this, but it's not really necessary. We match, like we find all the persons, and then we bring this down, and then do order by, and then return. But this can be done in a much more easier way. So usually the with is used when you have aggregations. So we can do something like this: match person and return the name, and order by the age, and descendingly, and we only want the top 3. So that's very similar to what MongoDB or SQL is able to do. Okay, yeah, another thing is Neo4j has array data type, and then we need we do need special way to handle the array sometimes. Sometimes it can be handled in the same way as like a simple type, but sometimes we do need a special way to handle it. So first, array literal is written in a similar way as in majority of the programming language. We use square bracket to indicate its array, and then each element, separated by a comma. So the array of integer and array of string. So both node and relationship, they can have property of the array type, like here. Assuming a person may play multiple roles, so we use array type as the data type of this property, like rows, or like this. Like a person's, if we want to updating existing node with array properties like this, so we just use array literals. So if we want to add the phone property of the person called Tom Hanks, and we can do it. First we find the person, and then we set its property form to an array. Okay, yeah, and similar to MongoDB and probably SQL, in array type, there are 2 special operators, in operator and unwind operator. It can be used to handle array type. So the in operator is usually to check if something is in a value is in the array, right? So it's just in. It doesn't need like a dollar or something, not like in MongoDB. So if we want to find out who has played Neo in which movie, and then we can do something like this, where Neo is in. So first we still need to find like the relationship between a person and a movie, and the relationship is acted in. And then we want to see if Neo, the particular string, happens in the property r.row. And again, because we basically need all of this, A and R and M. So we need R here, and we need A and M here. So we give each thing in the pattern a name or a variable name. Okay, so that's in is for findings, if something is in the array, and then the unwind is doing the same thing. We can flatten an array into multiple rows. Each has a single value instead of like multiple values. So if we want to find like all the movies released in either this year or this year, so there are actually different ways of doing it. So here is we can unwind this as year, and we try to match this and where the released equals to the year, and then we return the title. But if the query only deals with a single array type, so using either unwind or using in can both will actually do the same thing. So this is like we unwind the array, but it can be done in something like this. So where m.release is in this array. Instead of unwinding it, we just use the in operator. So these two queries is basically doing exactly the same thing. Just write it in a slightly different way. This perhaps is more easy to understand. So unwind is more useful if you're dealing with like two arrays, and then you probably need to unwind one, and then to match the element in one array in the other array. So that's the more useful. So let's see this relatively more complex query where unwind is actually needed. Using in itself is not. So that's a query actually involves two arrays. It's basically we want to see who shares a phone number with Tom Hanks. So suppose Tom Hanks' phone number is an array, and some other person's phone number is an array, and we want to find the intersection of these two arrays. So we can use unwind here by basically flattening one array, and then see if we can find the element in another array. So now suppose we have another node, Meg Ryan, and then we set its phone number as this. There could be more. It's an array type, but currently only one element. But anyway, it's array type. So now we want to run the query to see who shares any phone number with Tom Hanks. So first we find Tom Hanks and we find his phone numbers, right? And so now we bring down both the Tom Hanks phone numbers as phones and also itself, because we don't want to find. We want to use this to make sure we're not finding Tom Hanks himself, because he himself will definitely have the same phone number. So now we bring down this, and now we unwind this as individual phone number, and then we try to find like from all the other persons, and see if this is now like a scalar value, and then see if it's in the phone, like this person's phone, which is an array. So this is an array, and this is an individual, like a simple type. And at the same time, n shouldn't be equal as m, so we're not looking for Tom Hanks himself. So only if it's a different person. Because when we do the match, it basically matches all the person, including this person. So that's the reason why we want to bring down n as well, is we want to use it here in the inequality. And then we return the name. So that's the person who is not Tom Hanks, but does have the same number. Okay, so Neo4j also support indexing, but it only for the node, not really for the relationship. So by having index, it will make the query much more efficient. And then the index has similar behavior as in relational database system or in MongoDB. And the creating index is quite simple. Like create index on this, like the person is the label, and we want to be it on the name property. And you can drop it as well. And this will be basically how index is used and will be covered in next week. So yeah, that's all for this week. And the lab is just practicing basic Neo4j.